In section 9.8, we'll be talking about the inverses of matrices, specifically the multiplicative inverse of matrices. That means what two matrices, when multiplied together, will give us what's called the identity matrix. The identity matrix is the matrix that has ones along its main diagonal and has zeros everywhere else. This example that we're looking at here is just a 3x3 identity matrix, but any identity matrix has ones along the main diagonal and zeros everywhere else. Now we have to be careful because when you multiply two matrices, let's say A times B or B times A, remember those don't give you the same thing necessarily because multiplication for matrices is not commutative, which means unlike numbers, when you do numbers, 2 times 5 is 10, and 5 times 2 is also 10. That is not true of matrices necessarily. A times B and B times A are not necessarily the same. So, what does that mean about inverses? It means that two matrices are inverses if, when you multiply them in both directions. So, A times its inverse equals the identity matrix, but it also has to work the other way around. The identity matrix times the original matrix also has to be the identity matrix. Now the question becomes, does a matrix have to have an inverse? And the answer is no. Not every matrix will have an inverse, just like not every function has an inverse. So, if you are given two matrices, how do you find out if they are inverses? Well, we have to multiply them together in both orders. If in both orders we get the identity matrix, then yes, they're inverses. But if even one of the multiplications of the two matrices does not give us the identity matrix, then they are not inverses. Let's look at these first two matrices. Again, we are asked to determine if these two matrices are inverses of one another. So let's start by multiplying the two matrices in the order that they already appear. So that means we would look at multiplying the matrix 2, 3, 1, 1 times the matrix -1, 3, 1, -2. So when multiplied together, we should also get another 2 by 2 matrix. If you weren't sure why, the first matrix was a 2 by 2. The second matrix was a 2 by 2. The multiplication can be done because the two inside ones match. Your result is the two outside dimensions, which is a 2 by 2. So that means our answer also has to be a 2 by 2 matrix. Remember, we get the first entry of our multiplication matrix by multiplying the first row and first column and adding as we go. So the first entry should be the 2 times -1, which is -2, added to the 3 times 1, which is 3. So -2 and 3 will give us a +1. Next, let's go to the first row and the second column. So first row, second column. Again, multiply and then add. So we're going to multiply the 2 times the 3, which is 6, added to, well, the 3 times the -2 is -6. Well, +6 and -6 will give us 0. So far it is looking like it's probably going to be the identity matrix, but we still have to keep going. Multiplying the second row by the first column. So 1 times -1 gets us -1, and 1 times 1 gets us 1. Well, -1 added to 1 will get us 0. Still looking like the identity matrix. Now we're going to do the second row, second column. Well, 1 times 3 gets us 3, and 1 times -2 gets us -2. Well, 3 and -2 adds up to 1. So what do we end up with? we do indeed, when we get 1 in that last element, we do get the identity matrix, at least in that direction. So far, we're halfway there. We think that they're going to be identities, but you have to try the other way around. So let's switch them around. So now I have to do the -1, 3, 1, -2 first, and then do the 2, 3, 1, 1 second. Well, so let's do the same thing. We again know for the same reasons that it'll still end up being another 2 by 2. So beginning, we'll start out with first row, first column. -1 times -2 gets us, -1 times 2 will get us -2. 3 times 1 gets us 3. Well, -2 and 3 gets us a +1. Keep multiplying. Now I've got to do, let's see, first row and first column, or second column, excuse me. So we'll do -1 times 3, which is -3, and 3 times 1 is 3. Well, -3 and +3 when added up will give us a 0. So far, so good. Let's go to our next one. Second row, first column. Well, that's going to give us a 2 times 1, which is 2, and a -2 times 1, which is -2. Well, 2 and -2 will give us 0. Continuing right along, let's do our second row and second column. Well, let's see what we get. We get a 1 times 3, which is 3, and a -2 times 1, which is -2. Well, 3 and -2, when added up, do get us a +1. So indeed, both directions do give us the identity matrix, which is the ones along the main diagonal for both of these. So because both multiplications give us the identity matrix, yes, they are inverses. So A is they are inverses. Yes. So how would you do this for B? You'd have to do the exact same thing all over again. So let's try problem B. Again, we'll start by multiplying the two matrices in the order they're already listed. So we'll start by multiplying 2, 1, 3, 2. 2, the other matrix, 2, 1, -3, 2. This is for problem B. Okay, again, we'll end up with a 2 by 2 matrix. So we'll start out by multiplying out the first row and first column. Well, 2 times 2 will give us 4, and 1 times -3 will give us -3. So 4 and -3 will get us a 1. So far, so good. Next, we're going to do first row, second column. We'll get 2 times 1, which is 2, and another 1 times 2, which is 2. Well, 2 and 2 actually gives us 4. And we can stop right there because we're already getting something that is not going to be the identity matrix. So, because we're going to get something that is not the identity matrix right off the bat, we can go ahead and say for B that they are not inverses.